In this video, we're going to estimate the power released by thunderstorms and then by tornadoes. So let's start by estimating the power released by thunderstorms. So we're given a few variables. The power released by thunderstorms is mainly driven by the condensation or the rainfall that it releases onto the ground and into the atmosphere. So the latent heat of condensation is 2.5 times 10 to the 6 joules per kilogram. The density of water is 1,000 kilograms per meter cubed. The rainfall per day, or sort of this rainfall flux term, is 1 centimeter per day. And the radius of the storm is 1,000 kilometers, so a pretty big storm. And of course, the power, the units of power is joules per second. So we need to take these variables and back out power or joules per second. So the way to do that is just to do some dimensional analysis with these variables and multiply or divide them in such a way that we get the units that we want. First, we're going to need an area term. So let's model the thunderstorm. It's just a circle. And we know the radius. It's 1,000 kilometers. So the area of the storm is a storm equals pi r squared, which is just the formula for the area of a circle. And that is just pi 100 kilometers squared. And so that gives us 3.14 times 10 to the 10 meters squared. Okay, so that's the area that our thunderstorm covers. Now, let's just do some dimensional analysis here, and let's get back units of power. So, power equals, and you can check my math as we sort of go along here, but latent heat times the density of water times the rain flux times F storm times the area of the storm. And because our units of time is in days and we want seconds, we need to multiply by a factor of 1 over 86400. That's just the number of seconds in the day. Okay, so if we were to sort of plug in our units here just to make sure it works, we have joules per kilogram times kilogram per meter cubed times meters per day. And 1 centimeter per day is equal to 0.01 meters per day. So we want things in standard SI units times meters squared. And so when we multiply all of this out, the meters cancel here, kilograms cancel here. We're given joules per day, and then we have our conversion factor where 1 day equals 86400 seconds. And so when we multiply this term onto this, we get the proper units. Okay, so this right here is the formula that we want to get the power of the thunderstorm. And when we plug all of these variables into this formula, let's just come over here, the power of the storm equals 9.09 times 10 to the 12. 9.09 times 10 to the 12 joules per second. Okay, so that right here is the power that is released by this particular thunderstorm. So we just found the power released by a typical thunderstorm, which was 9.09 times 10 to the 12 watts, where 1 watt has units of joules per second. Now we're interested in understanding the power released by a tornado. So a tornado is a rapidly rotating column of air that moves along the ground with a much smaller impacted surface area than, let's say, a typical thunderstorm. So let's model our tornado as just a cylinder with a height of 100 meters and a radius of 10 meters. So in order to estimate the power, we first need to understand the area, the volume of wind uptaken by the tornado, and then understand how to relate that volume to the kinetic energy of the air. So just a few variables. Let's just say the wind speed velocity is 100 meters per second, and the density of air is 1 kilogram per meter cube. So let's first calculate the surface area of this tornado, and then we can use this formula to calculate the volume of air, where volume is surface area times velocity times time, which gives you back units of meters cubed. Okay, so because this is just a cylinder, we can use the area formula for a cylinder, which is 2 pi RH plus 2 pi r squared. Now, when we plug our values from here into this formula, we get 6911.5 meters squared. So that is the surface area of the tornado wall. Okay, now the volume of air taken up by the tornado, again, is area times velocity times time. Now, just not to get too far ahead of ourselves, but because power is units of joules per 1 second, we can assess the time to just be 1 second. So time is 1, which means it essentially drops out of the formula. And so we really just have to worry about area and velocity. Well, we just calculated the area, and we know the velocity. So the volume of air is just 6911.5 times 100 meters per second. And that gives us 6.912 times 10 to the 5 meter cubed. All right, so that is the volume of air taken up by the tornado. All right, so kinetic energy per unit volume is just 1/2 density times velocity squared. So we know the density, it's just 1 kilogram per meter cube. We know the wind speed velocity, it's 100 meters per second. And we now know the volume of air. So this, just multiplied by the volume, gives you kinetic energy, which has units of joules. So we can go ahead and just say that kinetic energy per unit volume times volume gives you 1/2 rho v squared times the volume of air, which we just calculated to be this. And so that gives us kinetic energy equals 3.4 times 10 to the 9 joules. 3.4 times 10 to the 9 joules. Okay, and because we're just assessing this over 1 second, we can just divide this by 1 second to get power equals 3.4 times 10 to the 9 joules per second, which is the units of power that we're looking for. So in this case, over 1 second, our power is equal to the kinetic energy. So you might notice right off the bat that the power released by a tornado is less than the power released by a storm, However, when you sit outside and you watch a thunderstorm go by, typically buildings are being destroyed. But when a tornado rolls through, there's often a path of destruction. So why is that the case if the power of a tornado is less than the power of a thunderstorm? And the reason is that the areas affected are different. So if you were to take the area of the ground that's being affected by the tornado, and you divide the power by that area, and you did the same for the thunderstorm, you'd find that the power per unit area of the tornado is substantially larger than the power per unit area of the thunderstorm. But I'll leave that to you to do as an exercise. So that's it for this video and this video series. Thank you very much, and I'll see you later.